Please subscribe to support the channel. Have you ever looked up at the night sky and wondered how long it would actually take to reach those distant worlds? Mercury, Venus, Mars, or even Neptune? The answer isn't as simple as measuring miles on a map. It's a story of motion, timing, and cosmic precision. Every planet is constantly moving around the sun, and every spacecraft must follow a curved path through space, using gravity and careful planning to reach its destination. In this journey, we'll explore how long it truly takes to travel to each planet in our solar system, from the quick trips to Venus to the decade-long odysseys to Neptune, revealing not just distances, but the incredible patience and ingenuity that make interplanetary travel possible. Every great journey begins with a plan, and in the vastness of space, that plan is everything. When we talk about traveling to another planet, we're not just talking about pointing a rocket at a target and blasting off. We're talking about a meticulously calculated expedition that can take years of preparation before the spacecraft even leaves the launch pad. In this video, we'll explore not just the numbers behind those incredible voyages, but also the factors that make them possible. Because the question, how long does it take to reach each planet, has more than one answer. It depends on distance, speed, and perhaps most importantly, the design of the mission itself. Distance is the most obvious factor. The planets in our solar system are spread out like stepping stones across an unimaginably vast pond. At its closest, Venus can be about 38 million kilometers from Earth, a cosmic neighbor, relatively speaking. But Neptune, the farthest major planet, can be over 4 billion kilometers away. That's more than 100 times the distance to Venus. So naturally, the farther a planet is, the longer it takes to get there. But distance alone doesn't tell the whole story, because the planets are constantly on the move. By the time a spacecraft leaves Earth, both our planet and its target have already shifted along their orbits around the Sun. This means mission planners have to calculate not where the planet is now, but where it will be months or years in the future. Then there's speed, how fast a spacecraft can actually travel through space. Rockets are powerful, but even they have limits. Once a spacecraft escapes Earth's gravity, it coasts through space at a steady velocity, which is determined by the energy it was given during launch. Some spacecraft are designed for speed, taking a more direct path and reaching their destination quickly, while others follow slower, more fuel-efficient routes. For example, a fast mission to Mars could reach it in just over 6 months, while a slower one might take 9 months or more. On the other hand, missions to the outer planets like Jupiter or Saturn can take years, not because a spacecraft isn't moving fast, but because of the way the route must curve through the solar system. And that brings us to the third key factor, mission design. This is where science meets strategy. Space agencies like NASA and ESA don't just aim to reach another planet. They plan missions that can enter orbit, collect data, or even land. To do that, spacecraft often use gravity assists, slingshot maneuvers around planets that give them an extra boost of speed without using additional fuel. These gravity assists can dramatically change a spacecraft's trajectory and travel time. For instance, instead of flying straight to Mercury, which sounds simple but is actually incredibly difficult, NASA's Messenger spacecraft took multiple flybys of Earth, Venus, and Mercury itself to gradually slow down enough to enter orbit. Without those assists, it would have zoomed past the planet at such high speed that it couldn't have stayed to study it. Mission design also takes into account the type of spacecraft and its goals. A flyby mission, which just passes close to a planet to take measurements and photos, can get there faster since it doesn't need to slow down or enter orbit. But an orbiter or lander must decelerate and position itself carefully, which requires more time and energy. Every choice, from the launch window to the propulsion system, affects the final timeline. It's a cosmic puzzle of energy, distance, and precision. Throughout this journey, we'll look at how these three factors, distance, speed, and mission design, shape every interplanetary mission we've ever undertaken. We'll move step by step through our solar system, exploring the real-world examples that reveal how far we've come in our quest to explore the planets. From Mercury, the small, scorched world closest to the sun, to Neptune, the poled, windy giant at the farthest edge of sunlight. Each destination tells a different story about time and distance. You'll learn why Venus is one of the easiest planets to reach and why Mercury, though closer, is surprisingly more difficult. You'll see how missions to Mars have mastered a delicate balance between timing and trajectory. You'll discover why traveling to the gas giants, like Jupiter or Saturn, requires not only patience, but also incredible mathematical precision, and how the outer ice giants, Uranus and Neptune, remain distant mysteries that only a few spacecraft have ever glimpsed. And we'll even travel beyond, to the dwarf planet Pluto, a reminder that space exploration never stops at the boundaries of what's known. By the end, you'll see that how long it takes isn't just a measure of days, months, or years. It's a reflection of human ingenuity, of how we've learned to work with the laws of physics rather than against them. It's about understanding that in space, patience is just as important as power. We'll break down each mission and uncover the reasons behind its timeline, exploring the brilliant strategies that make interplanetary travel not only possible, but successful. So as we move forward in this cosmic exploration, keep in mind that every number you hear, every 6 months, every 7 years, every 12-year journey, represents more than just travel time. It represents the heartbeat of exploration, decades of research, years of planning, and the courage to send something fragile and human-made into the infinite unknown. Now that we've set the stage for our voyage and understand what determines how long it takes to reach another world, let's dive deeper into the next question. If we know the distances, the speeds, and the mission designs, why is it still so complicated to actually get there?
Space may look like a vast empty void, but when it comes to traveling through it, nothing is ever simple. The idea of flying straight from Earth to another planet sounds logical, like drawing a line from one point to another on a map. But in reality, the universe doesn't work that way. The planets aren't fixed in place. They're constantly moving, orbiting the sun at different speeds on different paths, tilted at different angles. If you tried to fly in a straight line to where Mars is right now, by the time you arrived, Mars would have already moved millions of miles along its orbit. So instead of flying directly toward a planet, spacecraft have to aim for where that planet will be when they finally reach its neighborhood. A kind of cosmic game of catch played across hundreds of millions of kilometers. That's the first reason why interplanetary travel is so complicated: timing and orbital mechanics. Scientists must calculate launch windows, specific periods when the alignment between Earth and the destination planet allows for the most efficient journey. These windows often open only once every few years. Miss it, and the spacecraft can't just turn around and try again. The planets will be out of position, and the amount of fuel required to make up the difference would be enormous. It's like trying to jump onto a moving carousel from another spinning platform. You have to leap at exactly the right moment, or you'll miss your target completely. Then there's the matter of curved paths. Spacecraft don't travel in straight lines. They follow elliptical orbits that curve around the sun. This is because both the spacecraft and the planets are under the constant influence of the sun's gravity. The moment a spacecraft leaves Earth, it becomes part of the sun's gravitational system, pulled and guided by that immense force. To reach another planet, it must essentially fall toward the sun and then outward again, adjusting its path through tiny bursts of propulsion. This dance of gravity and motion is described by orbital mechanics, a field of physics that allows mission planners to chart precise trajectories that take advantage of the natural movements of celestial bodies. Think of it this way. Imagine trying to cross a river where the current is constantly shifting. You can't just aim straight for the other side, you'd be swept downstream before you ever reached it. Instead, you aim ahead, letting the current carry you into the right position. In space, gravity is that current, and spacecraft trajectories are like carefully plotted paths across it. One of the most ingenious ways scientists use gravity to their advantage is something called a gravity assist or gravitational slingshot. This maneuver allows a spacecraft to gain or lose speed by passing close to a planet and using its gravity to change direction or velocity. It's one of the greatest tricks in the book of interplanetary travel. By approaching a planet from behind its orbital path, a spacecraft can effectively steal a tiny bit of the planet's momentum, catapulting itself to higher speeds without using additional fuel. The technique can cut years off a mission's travel time, or make it possible to reach planets that would otherwise be too far away for a single rocket to reach on its own. NASA has used this method many times. The Voyager missions, for example, are legendary for their use of gravity assists. Voyager 2's grand tour of the outer planets, Jupiter, Saturn, Uranus, and Neptune, was made possible by a rare planetary alignment that happens only once every 176 years. By flying close to each planet in sequence, Voyager 2 used their gravity fields to slingshot itself from one to the next, gaining enough energy to reach Neptune and eventually continue into interstellar space. Without gravity assists, the mission would have required enormous amounts of fuel and decades more time, an almost impossible feat for the technology of the 1970s. Even for inner planets, gravity assists are essential. When NASA sent the Messenger spacecraft to Mercury, it didn't head straight there. Instead, it took a winding path through the inner solar system, performing 6 flybys, 1 of Earth, 2 of Venus, and 3 of Mercury itself, over 6.5 years. Why? Because getting to Mercury isn't the problem. It's slowing down enough to stay there. Mercury orbits so close to the Sun that its gravitational pull accelerates incoming spacecraft, making it extremely difficult to enter orbit. Messenger had to use flybys to gradually reduce its speed until it could finally be captured by Mercury's gravity. It's a counterintuitive problem. The closer you get to the Sun, the harder it is to stop. This delicate balance between speed, distance, and gravity is what makes interplanetary navigation such a masterpiece of precision. Engineers must calculate not just where a spacecraft will be months or years from now, but how fast it will be moving, how the Sun's pull will alter its path, and how close it can safely get to planets during flybys. Even a tiny miscalculation, a fraction of a degree off course, can cause a spacecraft to miss its target by millions of miles. That's why trajectory corrections are planned along the way, with onboard thrusters making subtle adjustments to keep everything on track. Another factor that adds to the complexity is fuel efficiency. Every bit of fuel on a spacecraft matters, and it's not possible to simply top up once it's in space. So mission designers use the laws of physics to their advantage, crafting routes that maximize the spacecraft's momentum and minimize fuel use. These carefully planned pathways are known as home and transfer orbits, the most energy-efficient way to travel between 2 planets that orbit the same star. But even these orbits require patience. They take time because the spacecraft has to follow the slow curve of the Sun's gravity, spiraling outward or inward in a long arc rather than flying straight across the solar system. And as if that weren't enough, the space environment itself presents challenges. The Sun's radiation, micrometeoroids, and temperature extremes must all be considered when designing both the spacecraft and its route. Too close to the Sun, and the heat could destroy sensitive instruments. Too far, and solar power becomes too weak to sustain operations. Every path is a compromise between time, safety, energy, and the mission's scientific goals. So when we ask, why can't we just fly straight there? The answer is beautifully complex, because the universe is in motion, and everything, planets, spacecraft, even light, must obey its laws. Interplanetary travel isn't a straight shot across the void. It's a carefully choreographed waltz through a constantly moving, invisible web of gravity and time. Understanding these principles helps us appreciate just how extraordinary every space mission truly is. Each one is a triumph of precision, creativity, and the unshakable human desire to reach beyond our world. Now that we've seen why traveling to another planet is so complicated, let's explore how scientists actually measure those long, incredible journeys. Not in straight lines or simple distances, but in the timelines of real missions that have made the impossible possible. When scientists talk about how long it takes to reach another planet, they're not giving you a number pulled from a simple distance chart. They're giving you a story shaped by real missions, real data, and decades of experience navigating the solar system. Space is not static, and because of that, time itself becomes a dynamic measurement. You can't simply divide the distance from Earth to Mars by the speed of a rocket and call it done. The planets are moving, the spacecraft's path is curved, and its speed changes over time as it's pulled and pushed by gravity. That's why when astronomers or engineers estimate travel time, they don't rely on straight-line distances. Instead, they base their calculations on what's actually been achieved, the journeys that spacecraft have already made, the routes they've taken, and the methods that worked best.
Think of it like planning a road trip on a winding mountain road. You could take a ruler to a map and measure the distance as the crow flies, but you'd never actually travel that way.
You'd have to follow the roads that twist, climb, and curve around the terrain. Space is even trickier, because the terrain isn't mountains or valleys, it's gravity itself, shaping the paths of planets and spacecraft alike. Scientists measure travel time based on these realistic paths, using data from missions that have actually gone there. For example, when someone says it takes about 6 to 9 months to reach Mars, that figure comes from the history of missions that have successfully made the trip. Spacecraft like NASA's Mars Reconnaissance Orbiter, the European Space Agency's Mars Express, and the Curiosity rover mission. Each followed a slightly different trajectory, launched at a different time, and used its own unique propulsion system. By analyzing these real-life journeys, scientists can give an average or expected range for how long it takes under optimal conditions. This approach is far more meaningful than simply quoting distances. The distance from Earth to Mars, for instance, changes constantly. Sometimes it's as close as 54 million kilometers, and other times it's over 400 million kilometers away. That's a difference of more than 7 times. So travel time isn't fixed, it depends heavily on the relative positions of the planets at the time of launch. Scientists call this timing the launch window, and it's a critical part of every mission. For Mars, a favorable window comes roughly every 26 months, when the 2 planets line up on the same side of the Sun, close enough that a spacecraft can make the journey efficiently using a Hohmann transfer orbit. When scientists plan new missions, they study the data from earlier ones to refine their predictions. The more missions we've sent, the better we understand the mechanics of each route. This accumulated knowledge helps mission designers determine not only how long a new journey will take, but also how much energy it will require, how much fuel must be carried, and when the spacecraft should launch. Each mission becomes a stepping stone, improving our accuracy for the next. For instance, when NASA planned its mission to Jupiter, it didn't just calculate how long it would take to travel the distance. Instead, engineers analyzed the trajectories used by previous missions, like Pioneer 10, Voyager 1, and Galileo. Those missions revealed how powerful Jupiter's gravity field could be for assists, how solar radiation affected instruments that far from the Sun, and how long it would take to perform course corrections during the trip. All of this real-world information was used to plan newer missions, like Juno, which launched in 2011 and took almost 5 years to reach Jupiter. The duration wasn't chosen arbitrarily, it was the result of tested flight paths and physics that had already been proven to work. Another layer to how scientists measure travel time comes from mission objectives. A mission designed only for a quick flyby, to collect snapshots and brief data as it zips past, might take a much shorter route than one intended to enter orbit or land. A flyby doesn't need to slow down, so it can use a faster trajectory. But an orbiter must carefully match its speed to the gravity and position of the planet to be captured safely. So while the straight-line distance might be the same, the actual journey can vary widely in time. The Cassini mission to Saturn, for example, could have reached the planet faster by taking a direct route, but it would have required enormous amounts of fuel to slow down for orbital insertion. Instead, Cassini used a series of gravity assists from Venus, Earth, and Jupiter, extending its travel time to nearly 7 years, but saving a massive amount of energy. To make these estimates reliable, scientists rely heavily on trajectory simulations. Before any mission is launched, engineers run thousands of computer models to test possible routes, each with slightly different starting conditions, fuel limits, and planetary alignments. These simulations reveal how long each possible path might take, how much energy it would use, and what risks it would encounter. The chosen route, the one that balances efficiency, safety, and mission goals, becomes the basis for how long we say it takes to reach that planet. And once the mission actually flies, its progress is constantly tracked and compared with the predicted models, refining our understanding even further. Even so, not all missions follow the same rules. New technologies like ion propulsion and solar electric propulsion are beginning to change the game. These engines don't burn fuel in short bursts like traditional rockets. Instead, they emit a continuous, gentle thrust for months or even years. This allows spacecraft to gradually accelerate to higher speeds than chemical rockets ever could. However, because the acceleration is slow at first, missions using these systems can take longer to reach their cruising speed, meaning travel times can vary greatly depending on the propulsion method used. Future missions might reach the outer planets faster than ever thanks to these steady and efficient engines. But for now, our best measurements still come from the chemical rockets and gravity-assisted paths that have defined decades of exploration. And then there's the human element, not just in planning, but in perception. When we hear that it takes 6 years to reach Jupiter or 12 years to reach Neptune, those numbers might sound long, but they represent an astonishing mastery of interplanetary motion. Each timeline is a direct reflection of what humanity has achieved so far. Every minute that a spacecraft spends coasting between worlds is built upon generations of knowledge of how to harness gravity, of how to predict motion, and how to use mathematics to navigate a moving solar system with pinpoint precision. So when we measure travel time to a planet, we're not measuring empty space, we're measuring experience. Each figure represents the accumulated wisdom of decades of exploration, the countless calculations, the launch windows missed and met, and the small course corrections that keep a spacecraft perfectly on track. These times are a record of our progress as explorers, showing not only how far we've gone, but how much we've learned about moving among the planets. With that understanding, we can finally start our journey through the solar system. Beginning with Mercury, the smallest planet and the closest to the Sun, it may seem like it should be the easiest to reach, but as we'll see, appearances can be deceiving. Mercury, the first planet from the Sun, a world of extremes. At first glance, you might assume it's the easiest planet to visit. After all, it's the closest to Earth in terms of solar proximity when our orbits line up, and it sits right next to the Sun, practically in our cosmic backyard. But in the grand puzzle of interplanetary travel, Mercury is one of the most challenging destinations of all. Small, dense, and blisteringly hot on one side while freezing cold on the other, Mercury is a paradox, simple in appearance, yet fiendishly complex when it comes to reaching and exploring it. It's the smallest planet in our solar system, barely larger than Earth's moon. In fact, if you stood on Mercury's surface, the horizon would curve sharply beneath you, a reminder of just how compact this world truly is. With a diameter of about 4,880 kilometers, you could line up nearly 3 Mercuries across the width of our own planet. Yet despite its size, Mercury is surprisingly heavy for its dimensions, with a massive iron core that makes up over 80% of its volume. This dense interior gives it a strong gravitational pull for such a small planet, one of many characteristics that make it both fascinating and difficult to reach. Orbiting the Sun at an average distance of about 58 million kilometers, Mercury whips around its star at speeds exceeding 47 kilometers per second. A single Mercurian year, one full orbit around the Sun, lasts just 88 Earth days. But the planet's rotation on its axis is slow and strange. It spins 3 times on its axis for every 2 orbits it completes around the Sun. This unusual spin-orbit resonance means that a single day on Mercury, sunrise to sunrise, lasts about 176 Earth days. If you were standing on its rocky plains, the Sun would appear to crawl across the sky in slow motion, rising and setting just twice during one Mercurian year. These extreme conditions, rapid orbital motion, slow rotation, and intense gravity from the nearby Sun, create a uniquely hostile environment for spacecraft. Temperatures can soar above 430 degrees Celsius or 800 degrees Fahrenheit during the day, hot enough to melt lead, and plunge below minus 180 degrees Celsius or minus 290 degrees Fahrenheit at night. The absence of a thick atmosphere means there's no buffer between Mercury's surface and the harsh solar radiation that floods its landscape. It's a world of pure contrast, blinding sunlight on one horizon and inky black space on the other, with the Sun appearing to be twice as large as it does from Earth. But it's not the heat that makes Mercury so hard to reach. It's the Sun itself. Most people imagine that going inward toward the Sun should be easier than heading outward into the solar system. After all, the distance is shorter. But in orbital mechanics, closer doesn't mean easier. The Sun's immense gravity dominates everything nearby, pulling at any spacecraft that ventures too close. To reach Mercury and stay there, a spacecraft must slow down relative to the Sun's pull, effectively canceling out much of the orbital speed it inherited from Earth. And that's a monumental challenge. Here's why. When a spacecraft leaves Earth,
It's already moving around the sun at nearly 30 kilometers per second, the same orbital speed as our planet. To drop closer to the sun, it has to lose energy, essentially falling inward. But you can't just slam on the brakes in space. Every bit of velocity reduction requires fuel. And fuel is the most limited resource aboard any spacecraft. If a probe were to fly straight toward Mercury, it would arrive moving far too fast to be captured by the planet's weak gravity. Instead of entering orbit, it would slingshot right past and continue back into deep space. To solve this problem, mission planners have to design intricate flight paths that use other planets, and even Mercury itself, to gradually adjust speed and trajectory. These paths involve gravity assists, which help the spacecraft shed velocity and approach Mercury more gently. The result is a journey that takes years, not months, despite the relatively short physical distance. That's what makes Mercury such a tantalizing target. Close in distance, but far in difficulty. Mercury's proximity to the sun also creates another major obstacle: radiation and solar heat. Spacecraft traveling inward must endure intense solar energy, far greater than what probes to Mars or Jupiter ever face. The sunlight near Mercury is up to 11 times stronger than it is at Earth, meaning that every component on a spacecraft must be shielded from heat and radiation. Engineers design these probes with specialized materials and reflective sunshades, often orienting them at precise angles to prevent their instruments from overheating. The smallest miscalculation could destroy sensitive electronics or fry delicate sensors long before arrival. Despite all these challenges, Mercury holds an irresistible allure for scientists. It's a planet of clues, a frozen time capsule from the earliest days of our solar system. Because it's so close to the sun, Mercury's surface has remained geologically quiet for billions of years, preserving a record of ancient impacts and tectonic activity. Studying it helps researchers understand how rocky planets form and evolve, offering insights into not only Mercury itself, but also Earth, Venus, and Mars. Its massive iron core, magnetic field, and mysterious surface composition raise questions about why it's so dense, why its crust looks so ancient, and what it can tell us about the sun's early influence on the planets. Only a handful of missions have dared to visit Mercury, and even fewer have successfully entered its orbit. Those that have managed to reach it have expanded our understanding in extraordinary ways, but they've also revealed just how unforgiving this tiny world can be. It's a planet that demands patience, precision, and respect. In the next segment, we'll follow the story of one such mission, NASA's Messenger spacecraft, a triumph of engineering and persistence that took 6.5 years to complete its long, spiraling journey to Mercury. Through its experience, we'll see why getting to the smallest planet in our solar system is one of the biggest challenges in space exploration. When NASA set out to explore Mercury in greater detail, it faced a problem that had stumped scientists and engineers for decades. How do you send the spacecraft to the planet closest to the sun without letting it fall helplessly into the sun's gravity well? The answer would become one of the most carefully orchestrated interplanetary dances ever performed. A journey that proved that even a short trip across the solar system can take years when precision is the goal. That journey belonged to Messenger, short for MES and SENGER, short for Mercury Surface, Space Environment, Geochemistry, and Ranging. Launched on August 3, 2004, Messenger's mission was to map Mercury's surface, study its magnetic field, and analyze its composition to uncover how such a small, dense planet could have formed so close to the sun. But before it could do any of that, it had to get there, and that turned out to be a monumental task. The direct distance between Earth and Mercury isn't enormous compared to the outer planets. In theory, if you could travel in a straight line, a fast spacecraft might reach Mercury in a few months. But in practice, the sun's gravity makes that impossible. Any spacecraft leaving Earth is already moving at about 30 kilometers per second relative to the sun, the same speed Earth travels in its orbit. To drop inward toward the sun,
the spacecraft has to slow down by tens of thousands of kilometers per hour, essentially canceling out a huge portion of its orbital momentum. But there's no giant space brake to press. Every bit of speed reduction requires fuel, and fuel is the most limited resource aboard any spacecraft. If a probe were to fly straight toward Mercury, it would arrive moving far too fast to be captured by the planet's weak gravity. Instead of entering orbit, it would slingshot right past and continue back into deep space. Instead, NASA's engineers designed Messenger's flight path as a series of calculated gravitational maneuvers, using other planets to bleed off its excess speed in stages. The mission's trajectory was a masterpiece of orbital mechanics, relying on 6 flybys over 6.5 years before finally entering Mercury's orbit in March 2011. The spacecraft's first major maneuver came just a year after launch, a flyby of Earth in August 2005. This pass didn't just adjust Messenger's path, it used Earth's gravity to slingshot the spacecraft inward, setting it on a new course toward Venus. By doing so, it saved a tremendous amount of fuel while helping align Messenger's trajectory closer to Mercury's orbital plane. Next came 2 flybys of Venus, one in October 2006 and another in June 2007. These encounters were critical. By looping around Venus, which orbits closer to the Sun, Messenger shed even more energy, gradually reducing the size of its orbit and moving it closer to Mercury's path. But every maneuver required patience. The spacecraft has to complete long arcs around the Sun between each encounter, sometimes taking more than a year to reach the right position for the next step. After its Venus encounters, Messenger wasn't finished, not even close. To fine-tune its trajectory and further slow down, it performed 3 separate flybys of Mercury itself in January 2008 and October 2008, and finally in September 2009. Each of these passes brought the spacecraft closer to matching Mercury's speed around the Sun, allowing it to map parts of the planet's surface even before going into orbit. During these flybys, Messenger captured thousands of images, revealing vast cratered landscapes, massive cliffs known as scarps, and strange surface features that suggested volcanic activity in Mercury's distant past. Only after all those maneuvers, 1 around Earth, 2 around Venus, and 3 around Mercury, was Messenger finally slow enough to be captured by Mercury's gravity. On March 18, 2011, nearly 6.5 years after leaving Earth, it fired its main engine for about 15 minutes, easing into a near-polar orbit around the small, sun-scorched planet. That moment marked a triumph of physics, patience, and persistence, a testament to how hard it is to go down the Sun's gravity well. Messenger's mission didn't just prove that reaching Mercury was possible, it showed just how much planning and endurance such a mission requires. The spacecraft had to survive years of exposure to extreme heat and cold, navigating a region of the solar system where the Sun's radiation is 11 times stronger than on Earth. It used a highly reflective ceramic sunshade to protect its instruments, maintaining internal temperatures within safe limits while the exterior baked under relentless sunlight. The smallest miscalculation could destroy sensitive electronics or fry delicate sensors long before arrival. Once in orbit, Messenger began a groundbreaking scientific campaign that lasted more than 4 years. It mapped 100% of Mercury's surface, discovered evidence of water ice hidden in permanently shadowed craters near the poles, and revealed unexpected geological features that suggested the planet had shrunk slightly as its core cooled over billions of years. Its data reshaped our understanding of Mercury not as a dead, inert world, but as a geologically dynamic planet with a complex history. Messenger's long journey also served as a reminder that in space exploration, time is as valuable a resource as fuel. The mission could have reached Mercury faster if it had carried more propellant, but doing so would have made it too heavy to launch. Instead, engineers traded time for energy, using the natural motion of the planets to their advantage. The result was one of the most elegant orbital insertions ever executed. To appreciate how extraordinary this is, consider that Messenger traveled more than 7.9 billion kilometers over the course of its mission.
not because Mercury is far away, but because of the intricate series of loops and orbits required to match its speed. Every flyby was timed within seconds. Every trajectory tweak carefully calculated years in advance. A single error could have meant missing Mercury entirely.
By the time Messenger's fuel ran out in 2015, it had completed over 4,000 orbits of Mercury, sending back more than 270,000 images and rewriting textbooks about the innermost planet. Its final act came when it crashed intentionally onto Mercury's surface, leaving a small impact crater, a lasting mark of human ingenuity on one of the most elusive worlds in our solar system. Messenger's 6.5-year voyage remains a perfect example of how travel time in space depends on more than distance. It's a delicate balance between speed, fuel, and the invisible forces that govern motion around the sun. What might look like a short hop inward is, in truth, a carefully choreographed ballet lasting years, a slow spiral of precision that brings us ever closer to the heart of our solar system. And just as Mercury's journey taught us patience, the next stop on our voyage, Venus, our nearest planetary neighbor, shows us how proximity can make travel faster, but the planet itself far more unforgiving. Venus, often called Earth's twin, is the second planet from the Sun and the closest planetary neighbor to our own world. It's similar in size, mass, and overall composition to Earth, which is why scientists have long been fascinated by it. With a diameter of about 12,104 kilometers, Venus is only slightly smaller than Earth, and its gravity is roughly 90% of what we experience here at home. On paper, it might seem like the most familiar of alien worlds, a planet that could almost feel like a sister to Earth in the cosmic family. But appearances can be deceiving. While Venus shares some physical characteristics with our planet, its environment is among the harshest in the solar system. Its thick, toxic atmosphere is composed primarily of carbon dioxide, with clouds of sulfuric acid that reflect sunlight and trap heat in an extreme greenhouse effect. Surface temperatures reach a scorching 465 degrees Celsius, 870 degrees Fahrenheit, hot enough to melt lead, and the atmospheric pressure is over 90 times that of Earth, equivalent to being nearly a kilometer beneath the ocean on our planet. The crushing heat and dense, corrosive air make Venus both awe-inspiring and incredibly hostile to spacecraft. Despite these challenges, Venus's similarities to Earth make it an irresistible target for study. Scientists are eager to understand why two planets that started out with similar sizes and compositions evolved so differently. Why does Venus have such a runaway greenhouse effect? Why does it rotate in the opposite direction of most planets, including Earth? Why is there no water on its surface today, even though there is evidence it may have had oceans in the distant past? Studying Venus helps us answer fundamental questions about planetary formation, climate evolution, and even the potential fate of our own world if greenhouse gases were left unchecked. Venus is also easy to spot from Earth, often glowing brightly in the sky as the morning star or evening star. Its thick clouds reflect sunlight efficiently, making it the third brightest natural object in the sky after the sun and the moon. Because of its brightness and proximity, Venus has been known and studied since ancient times, inspiring myths, navigation, and early astronomy. Yet, for all its familiarity in the night sky, reaching Venus with a spacecraft presents its own unique challenges, although in a different way than Mercury. Unlike Mercury, which is difficult to slow down due to the sun's gravitational pull, Venus's orbit makes it relatively more straightforward to reach. Its position, roughly 108 million kilometers from the sun, places it slightly closer to Earth than Mercury on average, and it doesn't have the same extreme speed around the sun. Spacecraft can travel to Venus using more direct trajectories without the need for as many complex flybys to shed speed. This relative accessibility has made Venus a frequent target for interplanetary missions over the past several decades, from early flybys and orbiters to landers that touched its scorching surface. Venus is also a planet of extremes in its rotation. Unlike Earth and most other planets, Venus spins retrograde, meaning it rotates in the opposite direction of its orbit around the Sun. One day on Venus, a full rotation on its axis, lasts about 243 Earth days, which is actually longer than its 225-day year. Curiously, this flow rotation means that its day is longer than its year. Yet, because of the retrograde motion, the sun rises in the west and sets in the east. These unusual dynamics contribute to Venus's extreme climate, including super-rotating winds in its atmosphere that can reach speeds of over 360 kilometers per hour, whipping around the planet much faster than the planet itself rotates. The combination of size, composition, proximity, and rotation makes Venus a particularly interesting target for interplanetary exploration. Its similarities to Earth provide a scientific mirror to study our own planet's past and future, while its harsh conditions push the limits of spacecraft design and mission planning. Unlike Mercury, which is small and technically challenging due to orbital mechanics, Venus is relatively easier to reach, but presents an environmental gauntlet that only specially designed probes can survive. Over the decades, human missions to Venus have revealed stunning insights. Thick cloud hiding a hellish surface, volcanic plains, massive shield volcanoes, and hints of tectonic activity. Despite its inhospitable environment, Venus has offered a window into planetary evolution, helping us understand not only the fate of rocky planets, but also the mechanisms that can turn a seemingly Earth-like world into a scorching inferno. In the next segment, we'll explore Venus travel time, examining why missions to this nearby planet are relatively quick compared to Mercury or the outer planets, and how spacecraft like Mariner 2 and others manage to reach it in mere months. Traveling to Venus is a unique case in the story of interplanetary exploration. Unlike Mercury, which requires years of careful orbital maneuvers and multiple gravity assists to slow down enough to enter orbit, Venus is much more accessible from Earth. Its position, the relatively moderate gravitational environment, and its position in the inner solar system allow for spacecraft to reach it far quicker. Missions to Venus have historically been among the shortest interplanetary journeys ever undertaken, with travel times measured in months rather than years. The first very successful mission to Venus was Mariner 2, launched by NASA in August 1962. At the time, humanity had only recently begun to venture beyond the bounds of Earth's orbit, and the challenge of sending a spacecraft to another planet was enormous. Yet Mariner 2 accomplished this incredible feat, arriving at Venus in December of the same year, a journey of just 4 months. This remarkable speed was possible because Mariner 2 followed a relatively direct trajectory, taking advantage of the launch window when Earth and Venus were favorably aligned. The spacecraft traveled over 100 million kilometers, coasting through space while gradually adjusting its path using the minimal onboard propulsion required for course corrections. Mariner 2's success paved the way for subsequent missions, demonstrating that inner planets could be reached quickly if the timing and trajectory were optimized. Later missions, including the Soviet Venera series and other American probes, typically took around 6 months to reach Venus. These travel times varied slightly depending on the precise launch date, the spacecraft's speed, and its trajectory. Unlike missions to Mercury or the outer planets, which must rely on complex gravity assists to slow down or gain energy, Venus missions can generally fly more direct paths, coasting along a home-and-transfer orbit, the most energy-efficient route between two planets with similar orbital planes. The speed of Venus missions is one of the factors that makes it so appealing for early planetary exploration. While the surface is inhospitable, spacecraft can reach the planet in a matter of months rather than years, allowing missions to send back critical data relatively quickly. For example, the early Venera flybys and orbiters launched by the Soviet Union in the 1960s and 1970s returned detailed measurements of Venus's atmosphere, pressure, and temperature in just half a year after launch. Similarly, NASA's Magellan mission, which mapped Venus's surface with radar in the 1990s, benefited from relatively short transit times, allowing the mission team to plan and execute observations efficiently. It's worth noting that the quick travel to Venus is primarily due to its position relative to Earth. Being the second planet from the Sun, Venus's orbit is closer to Earth's than Mercury, which orbits even closer to the Sun. Mercury's high orbital speed around the Sun makes it harder for spacecraft to slow down and match its motion, which is why it requires complex maneuvers over many years. Venus, in contrast, moves more slowly relative to a spacecraft leaving Earth, and is far enough from the Sun that gravitational acceleration is manageable. This combination of moderate distance, favorable orbital speed, and simpler gravity interactions allow for the much shorter travel times.
The short transit to Venus also influences mission design. Spacecraft need to be prepared for intense solar radiation and the thick atmosphere, but they don't require the extensive series of flybys or extreme fuel management strategies necessary for reaching Mercury or the outer planets. This makes Venus an excellent training ground for planetary missions, allowing engineers and scientists to test instruments and technologies in a hostile environment without committing to the long timelines of outer solar system missions.
In practical terms, a mission to Venus offers a rare combination: a nearby planetary neighbor that can be reached in months, providing a wealth of scientific data while remaining within the reach of relatively short-term mission planning. The speed of transit allows for quick turnarounds, timely analysis, and even the possibility of multiple missions in a relatively short span of time. For example, during the 1960s and 1970s, multiple Venus missions were launched in rapid succession, benefiting from repeated launch windows spaced roughly 2 years apart, each returning invaluable scientific discoveries. In contrast, missions to Mars, Jupiter, and beyond require a far longer commitment of time and resources, which changes the dynamics of mission planning, cost, and risk. Venus stands out as one of the rare planets where humans can quickly send probes, analyze results, and plan subsequent missions without the multi-year or decade-long timelines that characterize most other planetary explorations. In short, the journey to Venus demonstrates that interplanetary travel isn't always measured in years or decades. With the right trajectory, timing, and understanding of orbital mechanics, spacecraft can travel the vast distances of the solar system in mere months. Mariner 2's 4-month journey, followed by subsequent missions averaging about 6 months, set a standard for efficient interplanet travel, proving that proximity, combined with precise planning, can make even the hostile Venus surprisingly accessible. With Venus explored and travel times understood, our gaze now turns outward to Mars, the most studied planet after Earth and the most compelling target for future human exploration. Its combination of scientific intrigue and accessibility makes it the next step in our journey across the solar system. Mars, often called the Red Planet, occupies a special place in humanity's imagination. With its rusty, reddish surface, towering volcanoes, deep canyons, and polar ice caps, Mars has fascinated astronomers, scientists, and dreamers for centuries. Unlike Venus, which is shrouded in thick clouds and extreme heat, or Mercury, which is scorching by day and freezing by night, Mars presents a more approachable world. One that, while harsh and unforgiving, has conditions that are somewhat familiar. It is the most explored planet after Earth and stands as the leading candidate for future human colonization, making it the centerpiece of modern space exploration. Mars is roughly half the diameter of Earth, with a surface area about equal to the total landmass of our planet. Its gravity, about 38% that of Earth, is low enough to allow humans to move and potentially work efficiently, but strong enough to prevent the health issues associated with microgravity in space. Mars has seasons, polar ice caps, and a day length remarkably similar to Earth. One Martian day, or sol, is approximately 24 hours and 39 minutes. These Earth-like features, combined with evidence that liquid water once flowed on its surface, have made Mars a prime focus for scientists seeking to understand planetary evolution, the potential for past life, and the feasibility of future human settlement. Over the decades, Mars has been studied extensively by telescopes, orbiters, landers, and rovers. Its surface reveals a world shaped by both catastrophic and gradual forces. Enormous volcanoes like Olympus Mons, the largest volcano in the solar system. The vast Valles Marineris Canyon system, which stretches thousands of kilometers. And signs of ancient riverbeds and lakebeds, hinting at a wetter, potentially habitable past. Mars's atmosphere, composed mostly of carbon dioxide, is thin, averaging just about 1% of Earth's atmospheric pressure, which poses significant challenges for both robotic and potential human explorers. Yet the combination of its manageable gravity, familiar day-night cycle, and hints of water make it the most promising destination beyond Earth. Mars is also the planet of human ambition.
For decades, it has been the focal point of missions designed not only to study the planet, but also to test technologies for long-duration spaceflight. Rovers like Spirit, Opportunity, Curiosity, and Perseverance have traversed its surface, uncovering crucial insights about the planet's geology, climate, and potential habitability. Orbiters like Mars Reconnaissance Orbiter and MAVEN have provided detailed maps, atmospheric data, and high-resolution imagery, giving scientists the information needed to plan safe landings and explore the planet's mysteries. Every mission adds another layer to our understanding, gradually turning Mars from a distant dot in the sky into a tangible, reachable world. The red planet's allure isn't purely scientific, it's also symbolic. Mars represents the next step for humanity, the first destination where humans could live beyond Earth, at least temporarily. Unlike the gas giants or the icy outer planets, Mars has conditions that, with technology and planning, could support human life. Its proximity to Earth relative to the outer planets allows for missions with durations measured in months rather than years, making supply lines, communication, and eventual colonization feasible. However, Mars presents unique challenges as well. Its thin atmosphere offers little protection from radiation and micrometeoroids, meaning future astronauts would require substantial shielding. Dust storms can engulf the entire planet, affecting both solar-powered machinery and atmospheric measurements. And while liquid water is rare today, it exists primarily as ice beneath the surface or in transient briny flows, making access and usage a major engineering challenge. Yet despite these obstacles, Mars remains within humanity's reach in a way that other planets simply are not. Mars's status as the most explored planet after Earth is the result of decades of methodical, carefully planned missions. Its relative proximity, Earth-like features, and scientific intrigue have made it a proving ground for technology, a laboratory for understanding planetary history, and a beacon for future human exploration. From orbiters mapping its surface to rovers analyzing rocks and soil, each mission is a stepping stone toward the ultimate goal: sending humans to the red planet to walk across its plains, scale its volcanoes, and perhaps even build the first permanent off-world settlements. In the next segment, we'll examine Mars' travel time, exploring how most missions take 6 to 9 months to reach the planet, and how factors like launch timing, trajectory, and orbital mechanics influence the duration of this incredible journey. Traveling to Mars may seem simpler than reaching Mercury or the outer planets, but it still requires careful planning, precise timing, and a deep understanding of orbital mechanics. Unlike Venus, which can be reached in as little as 4 to 6 months, Mars lies farther from Earth at an average distance of about 225 million kilometers, and its orbit around the Sun is slightly tilted relative to ours. Because both planets are constantly moving, reaching Mars isn't simply a matter of pointing a spacecraft in its direction. It's about predicting where Mars will be months later and launching at the perfect moment to meet it along its path. Most missions to Mars are planned using what is known as a Hohmann transfer orbit, the most energy-efficient route between two planets. This method involves sending a spacecraft into an elliptical orbit around the Sun that intersects both Earth's orbit and Mars's orbit. Timing is everything. If the launch occurs too early or too late, the spacecraft could arrive too soon or too late, missing Mars entirely. These launch windows occur roughly every 26 months, when Earth and Mars are optimally aligned. By taking advantage of these windows, spacecraft can minimize the amount of fuel required while ensuring they reach their destination in a reasonable time frame. Using this approach, most missions take 6 to 9 months to travel from Earth to Mars. The variation in travel time depends on several factors, including the spacecraft's velocity, its exact trajectory, and any additional maneuvers needed along the way. For example, NASA's Mars Science Laboratory, which carried the Curiosity rover, launched in November 2011 and arrived at Mars in August 2012, a journey of about 8.5 months. Similarly, the Mars Reconnaissance Orbiter, launched in August 2005, reached Mars in March 2006, taking approximately 7 months. These durations reflect the careful balance between speed, fuel efficiency, and trajectory planning that characterizes Mars missions. Trajectory adjustments along the way are another crucial factor in travel time. Even when the spacecraft is on the correct home and transfer orbit, small course corrections are often required to ensure it intersects Mars' orbit precisely. These adjustments, known as mid-course corrections, are typically performed using small thrusters and are planned in advance. They allow mission controllers to compensate for tiny variations in launch speed, gravitational influences from other planets, or minor navigational errors. Although these maneuvers don't significantly alter the total travel time, they're essential for ensuring the spacecraft arrives safely and accurately at its destination. The relative speed of the spacecraft also affects travel duration. Faster trajectories can shorten the journey to around 6 months, but they require more fuel and precise calculations to avoid overshooting Mars. Slower trajectories, which use less energy, may extend the travel time to 9 months or more. Mission designers must weigh these factors carefully. Shorter travel times reduce exposure to cosmic radiation and allow for quicker mission execution, but they come at the cost of increased fuel consumption and stricter launch precision. In addition to orbital mechanics and speed, Mars's distance from Earth varies depending on the planet's positions and their respective orbits. When Earth and Mars are closest together, a configuration called opposition, the distance can shrink to around 54 million kilometers. Conversely, when the planets are on opposite sides of the Sun, the distance can exceed 400 million kilometers. This variation affects the required trajectory and, consequently, the travel time. Launching during optimal windows not only reduces the energy required, but also ensures the spacecraft spends the minimum possible time in transit. Human missions to Mars will likely follow similar principles, but will face even more constraints. Unlike robotic probes, which can endure months of isolation and operate with minimal life support, humans will require a trajectory that balances speed, safety, and resource management. Shorter travel times are preferable to reduce radiation exposure and life support demands, but faster trajectories require more powerful propulsion systems. Engineers are actively researching advanced propulsion methods, such as nuclear thermal or electric propulsion, to potentially cut travel time to Mars well below the 6-month minimum required by current chemical rockets. Mars missions also benefit from the fact that the planet is relatively easy to navigate once a spacecraft arrives. Unlike the gas giants, which require years of gravity assists and careful orbital insertion, Mars has a weaker gravitational field and a thin atmosphere. This allows orbiters and landers to enter orbit or descend to the surface using relatively straightforward aerobraking techniques or parachute-assisted landings. While challenging, these maneuvers are far less time-consuming than the multi-year approaches needed for planets like Jupiter, Saturn, or Mercury. In summary, reaching Mars is a carefully timed and precisely executed journey. Travel times range from 6 to 9 months, influenced by launch timing, trajectory design, spacecraft velocity, and in-flight course corrections. This balance of distance, speed, and mission planning has allowed humanity to send dozens of missions to the Red Planet over the past several decades, gradually building a wealth of knowledge about its atmosphere, surface, and potential for supporting life. Every successful Mars mission demonstrates the power of precision and patience, showing how careful planning can turn hundreds of millions of kilometers into a manageable voyage. With Mars understood both in terms of its allure and travel logistics, our gaze now shifts outward to Jupiter, the largest planet in our solar system and the first of the gas giants whose immense size and gravity present an entirely new set of challenges for interplanetary travel. Jupiter, the mighty king of our solar system, looms large in both size and significance. As the first of the gas giants beyond the asteroid belt, it represents a dramatic shift in the type of worlds we encounter as we journey outward from the Sun. Unlike the rocky inner planets Mercury, Venus, Earth, and Mars, Jupiter is a massive ball of gas and liquid, lacking a solid surface and dominated by turbulent storms, powerful magnetic fields, and a complex system of moons that rivals the planets themselves in diversity and intrigue. Its sheer size and distance make it one of the most captivating and challenging destinations for spacecraft, symbolizing both the power and mystery of the outer solar system. Jupiter is colossal. With a diameter of approximately 142,984 kilometers, it is more than 11 times wider than Earth and over 300 times as massive. Its volume is so vast that it could contain more than 1,300 Earths, yet it's composed mostly of hydrogen and helium, the same primary elements found in the Sun. This composition makes it a gas giant with no true solid surface to land on, but rather a gradual transition from gaseous outer layers to denser liquid hydrogen and, potentially, a solid or metallic core deep within. The enormity of Jupiter's atmosphere alone is staggering, with clouds stretching thousands of kilometers deep and swirling in bands driven by ferocious winds exceeding 600 kilometers per hour. One of the most iconic features of Jupiter is the Great Red Spot, a massive storm larger than Earth that has raged for at least 400 years. This tempest, along with countless smaller storms and vortices, gives the planet a dynamic, ever-changing appearance. Bands of clouds, striped in shades of white, brown, and red, race around the planet in opposite directions, creating turbulence and turbulence-driven waves that ripple across the atmosphere. Jupiter's atmosphere is also rich in chemical complexity, containing ammonia clouds, water vapor, and compounds that contribute to its striking coloration and the fascinating interactions of its weather systems.
Beyond its storms, Jupiter's gravitational influence makes it a pivotal player in the solar system. Its massive gravity affects the orbits of asteroids in the asteroid belt, shepherds groups of moons and ring particles, and even serves as a cosmic shield for the inner planets by deflecting or capturing comets and asteroids that might otherwise threaten Earth. This immense gravitational pull is both a blessing and a challenge for spacecraft. It can be used for gravity assists, boosting missions to more distant planets, but it also requires extreme precision when attempting to enter orbit or study the planet up close. Jupiter is also home to an extraordinary collection of moons, at least 95 confirmed so far, ranging from tiny asteroid-like rocks to massive worlds rivaling Mercury in size. Among these, the four largest moons, known as the Galilean moons, Io, Europa, Ganymede, and Callisto, are particularly remarkable. Io is the most volcanically active body in the solar system. Europa is covered in a thick ice shell with strong evidence of a subsurface ocean. Ganymede is the largest moon in the solar system and possesses its own magnetic field. And Callisto is heavily cratered and ancient, preserving a record of the early solar system. These moons have become primary targets for scientific exploration, as they may harbor conditions suitable for life and provide clues about planetary formation. Reaching Jupiter is an entirely different challenge from the inner planets. Its immense mass means strong gravitational forces, requiring spacecraft to carefully manage velocity and approach trajectories to avoid being flung off course. Located on average about 778 million kilometers from the Sun, more than 5 times the distance of Earth, Jupiter requires a longer journey, complex navigation, and strategic planning to achieve orbital insertion or even a close flyby. Its distance also means that travel times are measured in years rather than months, requiring missions to sustain themselves through the cold, radiation-filled expanse of the outer solar system. Despite these challenges, Jupiter has been a magnet for human exploration. It was the first gas giant ever visited by a spacecraft, and subsequent missions have revealed an extraordinary world of storms, magnetic phenomena, moons, and rings. Each encounter has expanded our understanding of gas giants, providing insights not only about Jupiter itself, but also about planetary systems beyond our own, where gas giants are commonly found. Studying Jupiter helps scientists understand planetary formation, atmospheric dynamics, magnetic field generation, and the gravitational interactions that shape entire solar systems. Jupiter represents the threshold between the inner rocky planets and the outer ice giants, standing both as a literal and symbolic gate to the deeper reaches of our solar system. Its massive size, dynamic atmosphere, and complex system of moons make it one of the most compelling targets for scientific inquiry, while the challenges of reaching and studying it test the limits of human ingenuity, precision, and perseverance. As we prepare to understand its travel time and the missions that have successfully reached it, we begin to appreciate just how vast and varied the solar system becomes once we move beyond Mars and into the realm of the gas giants. Next, we'll explore Jupiter travel time, examining missions such as Galileo and Juno, and how spacecraft have navigated the immense distances and powerful gravitational fields to study this colossal world. Saturn, the second largest planet in our solar system, is a world of breathtaking beauty and immense scale. Famous for its spectacular ring system, Saturn lies well beyond Jupiter, occupying an average distance of about 1.43 billion kilometers from the Sun.
While it is less massive than Jupiter, Saturn is no less impressive. Its diameter measures approximately 120,536 kilometers, making it more than 9 times wider than Earth. Its low density, so low that it could theoretically float in water, reflects its composition, a massive gas giant dominated by hydrogen and helium, with no solid surface for spacecraft to land on. Saturn is a striking reminder that the outer planets are as diverse as they are immense, each with its own unique set of features, challenges, and mysteries. Saturn is perhaps most famous for its rings, the most extensive and complex in the solar system. Composed of countless ice and rock particles ranging in size from tiny grains to massive boulders, these rings extend up to 282,000 kilometers from the planet, yet are astonishingly thin, often less than a kilometer thick. The rings are divided into several main segments, labeled A through G, with gaps like the Cassini division creating intricate patterns that dazzle astronomers and space enthusiasts alike. These rings are not static. They shift and interact, influenced by Saturn's moons and gravitational forces, creating waves, ripples, and even temporary ringlets that form and dissipate over time. Studying them provides insight into the dynamics of planetary ring systems and, by extension, the formation of planetary disks around young stars. Beyond its rings, Saturn's atmosphere is a swirling, dynamic environment. Cloud layers composed of ammonia, ice, and other compounds create striking bands and storm systems similar to Jupiter's, but often with a more subtle palette of colors. Winds in Saturn's upper atmosphere can reach speeds of over 1,800 kilometers per hour, making it the fastest spinning planet in the solar system. Enormous storms occasionally erupt, producing massive lightning flashes and turbulent atmospheric phenomena that can be observed even from Earth with telescopes. Saturn's gravitational influence is formidable, though less extreme than Jupiter's. Its mass and size allow it to dominate its immediate region of the solar system, shepherding moons and ring particles alike. Speaking of moons, Saturn is home to at least 145 confirmed satellites, ranging from small, irregularly shaped bodies to large, geologically complex worlds like Titan and Enceladus. Titan, Saturn's largest moon, is bigger than Mercury and possesses a thick nitrogen-rich atmosphere with lakes and rivers of liquid methane and ethane. Enceladus, on the contrary, is a smaller icy moon that ejects geysers of water vapor and ice particles, hinting at a subsurface ocean that could harbor the conditions for life. These moons make Saturn not just a giant planet to observe, but a rich system of worlds to study and explore. Reaching Saturn presents enormous challenges compared to inner planets or even Jupiter. Its distance from the Sun means spacecraft face extended travel times, typically measured in years rather than months, and must endure the cold, radiation, and sparse sunlight of the outer solar system. Solar power becomes less effective at this distance, requiring spacecraft to rely on radioactive thermoelectric generators or highly efficient solar arrays designed to function under low light conditions. The vast gravitational field of Saturn also necessitates careful navigation for orbital insertion and flybys, making missions to Saturn a careful balancing act of speed, fuel management, and trajectory planning. Saturn is also a planet of extremes in scale and phenomena. Its immense size and low density combine to create a world that is deceptively fluffy. Yet its gravity is strong enough to influence an enormous number of moons, ring particles, and passing asteroids. The interplay between these elements, planet, rings, moons, and the Sun's distant influence, creates a dynamic system that continues to captivate astronomers. Understanding Saturn is critical not only for studying gas giants in general, but also for learning about the processes that shape planetary systems, both within and beyond our own solar system. Saturn's allure goes beyond science. It has long inspired human imagination. Its rings, visible even through modest telescopes from Earth, have fascinated observers for centuries, leading to myths, legends, and the first attempts to understand planetary formation. Modern missions like Pioneer 11, Voyager 1 and 2, and Cassini-Huygens have transformed our understanding of Saturn, revealing a dynamic, active, and deeply complex world that continues to captivate and challenge our expectations. As we move toward understanding Saturn travel time, we will see how the enormous distance to this gas giant, combined with its powerful gravity and the desire for detailed scientific study, requires missions that take nearly a decade to reach the planet. From Cassini's carefully orchestrated gravity assist to the careful planning needed for orbit insertion, the journey to Saturn demonstrates the extraordinary combination of patience, engineering, and ingenuity necessary to explore the outer solar system. Reaching Saturn is no simple task. While its rings and moons make it one of the most alluring planets to study, the sheer distance from Earth, combined with its powerful gravity and location beyond Jupiter, makes the journey long, complex, and meticulously planned. The most iconic mission to Saturn, Cassini-Huygens, exemplifies the extraordinary patience and ingenuity required to explore the outer solar system. Launched on October 15, 1997, Cassini did not travel in a straight line. Instead, it took a carefully designed path that included multiple planetary flybys, an astrogee known as gravity assist, to gain speed and adjust its trajectory, ultimately taking nearly 7 years to reach Saturn. The basic problem of traveling to Saturn is distance. At an average of about 1.43 billion kilometers from the Sun, Saturn is nearly 10 times farther from Earth than Mars and almost twice as far as Jupiter. A direct trajectory would require an enormous amount of fuel to accelerate and then decelerate the spacecraft, far more than could be realistically carried aboard a single launch vehicle. To overcome this, Cassini's flight plan relied on a series of gravity assists from other planets, a clever technique that uses the gravitational pull of a planet to change a spacecraft's speed and direction without consuming additional fuel. Cassini's trajectory is often called the VV-EJGA route, an acronym for Venus, Venus, Earth, Jupiter Gravity Assist. In this path, the spacecraft first flew by Venus twice, in April 1998 and June 1999. These flybys helped Cassini gradually gain the velocity needed to reach the outer solar system. Each encounter required precise timing. Arriving too early or late would result in a missed boost or an incorrect trajectory, potentially sending the spacecraft into deep space or dangerously close to the Sun. After Venus, Cassini flew past Earth in August 1999, using our planet's gravity to gain even more speed and redirect its path toward Jupiter. The final gravity assist occurred with Jupiter in December 2000. This flyby served two purposes. It provided a massive velocity boost to propel Cassini towards Saturn and allowed engineers to fine-tune the spacecraft's trajectory for a precise arrival at the ringed planet. Over the next 6.5 years, Cassini traveled hundreds of millions of kilometers through the cold, dark expanse of the outer solar system, relying on onboard instruments and ground-based navigation teams to make small course corrections along the way. Cassini's journey was not merely about speed. Each flyby also presented opportunities to test instruments, collect data on the planet's and interplanetary environment, and refine techniques for navigation and communication across hundreds of millions of kilometers. All tests of engineering and operational endurance. On July 1, 2004, nearly 7 years after launch, Cassini finally arrived at Saturn. The spacecraft executed a carefully timed engine burn to slow down enough to be captured by Saturn's gravity, entering orbit for a mission that would last over 13 years. During its time at Saturn, Cassini revolutionized our understanding of the planet, its rings, and its moons. It revealed active geysers on Enceladus, mapped the thick atmosphere of Titan, studied Saturn's magnetic field, and provided breathtaking images of the rings, uncovering intricate structures, waves, and seasonal changes. Cassini's long travel time illustrates a fundamental principle of outer planet exploration. Distance, gravity, and energy constraints govern every mission decision. Unlike Mars or Venus, which can be reached in months using relatively straightforward trajectories, Saturn requires careful energy management and creative use of gravity assist to make the journey feasible. The 7-year cruise underscores the patience needed for deep space exploration, as well as the meticulous planning, precision engineering, and resilience required to sustain a spacecraft for such an extended voyage. Moreover, Cassini's mission highlights the balance between travel time and scientific reward. While nearly 7 years of travel may seem daunting, the mission's approach allowed engineers to conserve fuel, reach Saturn safely, and execute a complex orbital insertion, ultimately enabling a mission that returned unprecedented scientific discoveries. Without these carefully orchestrated gravity assists and long-duration planning, a mission of Cassini's magnitude would have been impossible, or at the very least, far more expensive and risky. In conclusion, Cassini's nearly 7-year journey to Saturn demonstrates the extraordinary challenges of reaching a planet in the outer solar system. The combination of immense distance, gravitational influences from multiple planets, and the need for precise navigation turned the voyage into a carefully choreographed ballet of physics and engineering. Through its journey, Cassini not only reached Saturn, but opened a new chapter in humanity's exploration of the outer planets, revealing a world of rings, moons, and dynamic systems far more complex than anyone had imagined. With Saturn explored in terms of both its allure and the journey required to reach it, our journey continues outward to Uranus, an icy giant with a unique sideways rotation and a system of moons that challenge our understanding of planetary formation and dynamics.
Uranus is one of the most enigmatic and unusual planets in our solar system. Known as an icy giant, it occupies a position far beyond Saturn, averaging a distance of about 2.87 billion kilometers from the Sun. Unlike the gas giants Jupiter and Saturn, which are composed primarily of hydrogen and helium, Uranus contains a larger proportion of ices, water, ammonia, and methane, mixed with hydrogen and helium. This composition gives it a distinctive blue-green hue caused by methane in its upper atmosphere absorbing red light and reflecting blue and green wavelengths. Uranus is a world that feels alien not just because of its distance, but because it defies many expectations about how a planet should behave. One of Uranus's most remarkable characteristics is its sideways rotation. Unlike Earth, Mars, or even Saturn, which spin roughly upright relative to the plane of the solar system, Uranus rotates on its side with an axial tilt of approximately 98 degrees. In practical terms, this means that its poles lie almost in the plane of its orbit, causing extreme seasonal variations. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness as the planet orbits the Sun over its 84-year-long year. This sideways spin is a cosmic oddity, likely the result of a colossal collision with an Earth-sized object early in the planet's history, tilting it dramatically and forever altering its rotational dynamics. Uranus is also an icy giant in contrast to the gas giants. Its interior structure consists of a rocky core surrounded by a deep layer of icy materials, water, ammonia, and methane, often referred to collectively as a mantle of ice. Above this layer lies an atmosphere of hydrogen, helium, and methane, giving the planet its characteristic color and masking the icy interior beneath. Despite its name, the ice inside Uranus is not necessarily frozen water as we know it. Under the high pressures and temperatures within the planet, it exists in a hot, dense, and highly pressurized fluid state, creating conditions that are vastly different from anything on Earth. Uranus's atmosphere, though relatively calm compared to Jupiter's or Saturn's, contains subtle banding, clouds, and occasional storms. High-altitude clouds of methane ice can appear as faint streaks or features, and localized storms occasionally disrupt the otherwise tranquil atmosphere. Uranus also has a weak magnetic field, unusual in its orientation, being tilted about 60 degrees relative to its rotational axis and offset from the planet's center.
This generates a unique and complex magnetosphere, shaped by the sideways rotation and the solar wind, making Uranus an intriguing subject for studies of planetary magnetism. The planet is surrounded by a system of 27 known moons, most of which are small, icy, and irregularly shaped. The largest moons, Titania, Oberon, Umbrio, Ariel, and Miranda, are geologically fascinating, exhibiting evidence of past tectonic activity, surface fractures, and, in Miranda's case, bizarre coronae that suggest a violent and geologically complex history. Uranus also has a faint system of rings, first discovered in 1977, composed of dark, narrow bands of dust and debris that orbit the planet in delicate arcs. Though not as prominent as Saturn's rings, Uranus's ring system adds to the mystique and complexity of the planet. Despite its beauty and uniqueness, Uranus is remarkably underexplored. Only a single spacecraft, Voyager 2, has visited Uranus, flying by in January 1986. This fleeting encounter provided the first close-up images of the planet, revealed its moons and rings, and gave scientists the only direct measurements of its atmosphere, magnetic field, and interior properties. Since then, Uranus has remained largely a distant, mysterious blue-green dot, tantalizing astronomers from afar with the promise of secrets hidden beneath its icy clouds.
Uranus's unusual rotation, icy composition, distant location, and faint rings make it one of the strangest and least familiar worlds in our solar system. It challenges our understanding of planetary formation and evolution, serving as a bridge between the gas giants of Jupiter and Saturn and the ice giants of Neptune. Exploring Uranus is not just a matter of distance, it is a journey into a world that behaves unlike any other, where seasons last decades, storms are muted yet mysterious, and moons hint at violent histories long past. In the next segment, we will discuss Uranus travel time, exploring how Voyager 2, the only spacecraft to have visited this icy giant, took about 8.5 years to reach it, and the challenges involved in planning a mission to such a distant and unique planet. Voyager 2 remains the only spacecraft to have ever visited Uranus, and its journey is a remarkable testament to both human ingenuity and the challenges of exploring the outer solar system. Launched on August 20, 1977, Voyager 2 was part of NASA's ambitious Voyager program designed to take advantage of a rare planetary alignment that occurs only once every 175 years. This alignment allowed a single spacecraft to visit Jupiter, Saturn, Uranus, and Neptune in a carefully planned sequence using gravity assists to slingshot from one planet to the next while conserving fuel and optimizing travel time. Reaching Uranus was a monumental task. The planet orbits at an average distance of about 2.87 billion kilometers from the Sun, more than 19 times the distance from Earth to the Sun. To reach it, Voyager 2 had to travel through the vast, cold, and largely empty expanse of the outer solar system, relying on a precise trajectory calculated years in advance. Unlike missions to the inner planets, which can be measured in months, the voyage to Uranus required patience, precision, and careful use of gravitational boosts from the planets it had already visited. Voyager 2's journey to Uranus took approximately 8.5 years, passing Jupiter in July 1979 and Saturn in August 1981 before finally reaching the icy giant on January 24, 1986. The spacecraft's approach was meticulously timed. It had to arrive when Uranus's orientation would allow for optimal imaging of the planet, its moons, and rings. The spacecraft also had to maintain its trajectory with incredible precision, as even minor deviations over billions of kilometers could have resulted in missing the planet entirely. One of the key tools that made this long journey possible was the use of gravity assists, sometimes called slingshot maneuvers. By flying close to Jupiter and Saturn, Voyager 2 gained additional velocity without using extra fuel, allowing it to reach Uranus in a reasonable amount of time. These maneuvers were not simple. They required detailed knowledge of the planet's positions, speeds, and gravitational fields, as well as careful planning to ensure the spacecraft remained on course for its next target.
Each gravity assist also provided opportunities for additional scientific observation, allowing Voyager 2 to study Jupiter and Saturn in unprecedented detail, while simultaneously setting itself up for the outer reaches of the solar system. The time Voyager 2 spent en route to Uranus highlights some of the logistical challenges of outer planet exploration. Even at high speeds, covering billions of kilometers in space takes years. Throughout the journey, the spacecraft relied on onboard instruments, gyroscopes, and thrusters to maintain orientation and trajectory while enduring the harsh environment of deep space, including extreme cold, cosmic radiation, and the increasing delay in communication with Earth, over 2.5 hours one way by the time it reached Uranus. Upon arrival, Voyager 2 provided humanity's first close-up look at Uranus and its moons, rings, and magnetic field. The spacecraft revealed a planet with a pale blue-green color, faint ring structures, and 10 new moons that had never been seen before. It measured Uranus's extreme axial tilt, its unusual magnetic field, and atmospheric conditions, giving scientists unprecedented insight into the structure and behavior of an ice giant. Voyager 2 also captured dramatic images of the planet's moons, from the geologically scarred Miranda with its strange corona to the icy surfaces of Titania, Oberon, and Ario. These observations transformed Uranus from a distant point of light in the sky into a richly detailed world. The 8.5 years it took Voyager 2 to reach Uranus underscore the realities of deep space exploration. Distance dominates everything. Travel times are measured in years, trajectories must be precise, and spacecraft must operate autonomously across vast stretches of space. Unlike missions to Venus or Mars, which take months, or even missions to Jupiter or Saturn, which take 5 to 7 years, Uranus sits at a distance where even the fastest, most efficient spacecraft must spend nearly a decade en route. This is why Uranus remains so mysterious. Opportunities for close-up exploration are rare, and the investment in time, resources, and planning is immense.
Voyager 2's journey also illustrates how travel time affects mission design. Engineers had to ensure the spacecraft could survive years of isolation, maintain its instruments, and continue collecting data despite the extreme conditions of the outer solar system. Every subsystem was tested to operate reliably for years without repair, and every scientific instrument was optimized to maximize data collection during the brief encounter with Uranus. The success of Voyager 2 in reaching Uranus and returning invaluable data is a triumph of long-term planning, engineering, and human vision. In summary, Voyager 2's 8.5-year journey to Uranus highlights the extraordinary challenges of outer solar system exploration. Distance, gravity, and time combine to make such missions rare, complex, and demanding. Yet the rewards are unparalleled. A close-up glimpse of a distant icy world with unique rotation, faint rings, and mysterious moons. Uranus remains a lonely sentinel in the outer solar system, patiently waiting for the next spacecraft that dares to continue what Voyager 2 began. Next, we will look at Neptune, the farthest major planet from the Sun, whose extreme distance and cold environment make it one of the most challenging destinations for spacecraft, and how Voyager 2 managed to reach it after Uranus. Neptune, the 8th and farthest major planet from the Sun, represents the outer boundary of our solar system's classical planets. Orbiting at an average distance of about 4.5 billion kilometers, nearly 30 times farther from the Sun than Earth, Neptune is a world defined by extreme cold, powerful winds, and a mysterious icy environment. Its position at the very edge of the Sun's influence means it receives only a fraction of the sunlight that Earth does, making it one of the coldest planets in the solar system. With average atmospheric temperatures plunging to -214 degrees Celsius or -353 degrees Fahrenheit, Neptune is a frozen, remote world that challenges both our imagination and the limits of spacecraft technology. Neptune is classified as an ice giant, like Uranus, with a composition dominated by water, ammonia, and methane ices.
in addition to hydrogen and helium. Unlike the gas giants Jupiter and Saturn, which are composed primarily of lighter gases, Neptune's dense mixture of ices and gases contributes to its smaller size relative to Jupiter and Saturn, while still making it more massive than Uranus. Its deep, high-pressure interior likely contains a hot, dense ocean of water, ammonia, and methane ice surrounding a rocky core, creating conditions vastly different from anything on Earth. The methane in Neptune's upper atmosphere absorbs red light and reflects blue, giving the planet its striking azure coloration. Despite its extreme distance, Neptune exhibits a surprisingly dynamic atmosphere. The planet is home to the fastest winds in the solar system, reaching speeds up to 2,100 kilometers per hour, over 1,300 miles per hour. These winds sweep around massive storm systems, some of which, like the historic Great Dark Spot observed by Voyager 2 in 1989, are comparable in size to Earth. Neptune also shows cloud bands and bright, high-altitude clouds of methane ice crystals that drift across its atmosphere, hinting at complex weather systems that remain largely mysterious due to the limited direct exploration of the planet. Neptune's system of moons and rings adds to its intrigue. It has 14 known moons, with Triton being the largest and most remarkable. Triton is geologically active, with geysers that spew nitrogen gas and ice, and it orbits Neptune in a retrograde path, suggesting it was likely captured from the Kuiper Belt. Neptune also has a faint and fragmented ring system, composed of dark dust and debris, which was discovered relatively recently compared to Saturn's and Uranus's rings. These features make Neptune not only a distant planet, but also a complex system with active moons and intriguing structures waiting to be studied. The remoteness of Neptune presents extreme challenges for exploration. At nearly 30 astronomical units from the Sun, it receives very little sunlight, making solar power largely ineffective for spacecraft. Communications take more than 4 hours for a signal to travel one way from Earth, requiring spacecraft to operate with high autonomy. Its distance also means that travel times are measured in decades rather than months, necessitating long-term mission planning, reliable systems, and an extraordinary commitment of resources. Only one spacecraft has ever visited Neptune directly, Voyager 2, emphasizing how rare and difficult missions to this icy giant are. Neptune's place at the outer edge of the classical solar system, its extreme temperatures, fast winds, and icy composition make it one of the most intriguing and challenging destinations for exploration. Studying Neptune is critical, not only for understanding the dynamics of ice giants, but also for shedding light on exoplanets, as planets similar to Neptune are among the most common types detected around other stars. Its unique characteristics provide a bridge between our understanding of the inner gas giants and the more distant icy bodies that populate the Kuiper Belt and beyond. In the next segment, we will examine Neptune travel time, detailing how Voyager 2 managed the long journey to this distant, frigid world and what it took in terms of planning, gravity assists, and patience to accomplish humanity's first and only close encounter with Neptune. Voyager 2's visit to Neptune represents one of humanity's most remarkable feats of interplanetary exploration, and it underscores the extraordinary challenges involved in reaching the outermost planets. After completing its encounter with Uranus in January 1986, Voyager 2 continued on its carefully planned trajectory toward Neptune, which lies on average 4.5 billion kilometers, nearly 30 times farther from the Sun than Earth. Traveling such vast distances required a combination of precise timing, careful navigation, and strategic use of gravity assists to reach its destination in a manageable timeframe. In total, Voyager 2's journey from Earth to Neptune took approximately 12 years, demonstrating the immense patience and planning required for missions to the outer solar system. The spacecraft's path to Neptune was designed to take advantage of the rare planetary alignment of the late 1970s, which allowed it to sequentially visit Jupiter, Saturn, Uranus, and finally Neptune. Each gravity assist provided by these planets was critical. By flying past Jupiter and Saturn in the late 1970s and early 1980s, Voyager 2 gained additional velocity and adjusted its trajectory to reach Uranus. And then after Uranus, it continued on a course toward Neptune without requiring excessive onboard fuel. These maneuvers highlight a central principle of deep space travel. When distances are so great, gravity becomes both a tool and a challenge, enabling spacecraft to traverse billions of kilometers with limited propulsion, while requiring extraordinary precision in calculations. The long travel time of 12 years also illustrates the challenges of maintaining a spacecraft over such extended periods. Voyager 2 had to operate reliably across immense distances, relying on a radioisotope thermoelectric generator for power, since solar panels will be ineffective in the faint sunlight of the outer solar system. Communication with Earth became increasingly difficult, with signals taking over 4 hours one way, meaning that real-time control was impossible. Engineers had to design Voyager 2 to operate autonomously for long stretches, performing critical navigation and system checks without immediate human intervention. Voyager 2 arrived at Neptune on August 25, 1989, providing humanity's first and only close-up view of the icy giant. During the flyby, the spacecraft captured detailed images of Neptune's dynamic atmosphere, revealing the Great Dark Spot, a massive storm comparable in size to Earth, as well as smaller storms and high-altitude methane ice crystals that drift across its atmosphere, hinting at complex weather systems that remain largely mysterious due to the limited direct exploration of the planet. It also discovered 6 previously unknown moons, mapped the faint ring system, and provided measurements of Neptune's magnetic field and gravitational characteristics. This wealth of data dramatically expanded our understanding of the outer solar system, demonstrating how a single, carefully orchestrated mission could illuminate a distant and previously mysterious world.
The 12-year journey to Neptune exemplifies the realities of deep space exploration: vast distances, slow transit times, and the necessity of meticulous planning. Unlike inner planets such as Venus or Mars, which can be reached in months, Neptune's remoteness means that every mission requires years of preparation, execution, and patience. Voyager 2's success depended not only on gravity assists and trajectory planning, but also on the spacecraft's resilience and the careful long-term management by the mission team. Every minor calculation and course correction over those 12 years was crucial. A small error could have resulted in a missed encounter with the planet, squandering a once-in-a-lifetime opportunity to study Neptune up close. Voyager 2's achievement also underscores the incredible scale of our solar system. While traveling to Mars might take half a year, and reaching Jupiter or Saturn can take 5 to 7 years, Neptune lies at such a remote distance that even the fastest spacecraft must spend over a decade in transit. This makes Neptune exploration a testament to both human patience and engineering brilliance, as well as a stark reminder of the challenges posed by the outer solar system. The information returned by Voyager 2 continues to inform planetary science, mission planning, and our understanding of ice giants, providing the only direct measurements we currently have of Neptune and its moons. In summary, Voyager 2's 12-year journey to Neptune highlights the extreme distances, careful trajectory planning, and long-term mission management required for outer solar system exploration. By taking advantage of gravity assists, autonomous navigation, and robust engineering, the spacecraft successfully reached the farthest major planet from the Sun and transformed it from a faint blue dot into a richly detailed world, complete with storms, rings, and moons. Neptune's remoteness makes future missions challenging but scientifically rewarding, and Voyager 2 remains a singular example of humanity's ability to explore even the coldest, most distant corners of our solar system. Looking beyond Neptune, we turn briefly to Pluto, the dwarf planet at the edge of the Kuiper Belt, where humanity's fastest spacecraft, New Horizons, demonstrated just how long it takes to traverse the outermost reaches of our solar system.
Beyond Neptune lies the distant, icy realm of the Kuiper Belt, a vast region filled with icy bodies and dwarf planets, among which Pluto is the most famous. Once classified as the ninth planet, Pluto is now recognized as a dwarf planet, but its intrigue and significance in planetary science remain undiminished. Orbiting the Sun at an average distance of about 5.9 billion kilometers, Pluto is a cold, small, and remote world, with a diameter of roughly 2,377 kilometers, less than one-fifth that of Earth. Its surface is composed of a mix of ice and rock, with nitrogen, methane, and carbon monoxide frost giving it a pale, textured appearance. Despite its small size, Pluto possesses a surprisingly complex atmosphere, seasonal changes, and a system of 5 known moons, the largest being Charon, which is nearly half Pluto's size and forms a unique binary-like system with the dwarf planet. Reaching Pluto presents challenges similar to, and in some ways greater than those for Neptune. Its extreme distance from the Sun makes solar power ineffective, requiring spacecraft to rely on radioisotope thermoelectric generators for energy. Communication delays are significant. A signal from Pluto to Earth takes over 5.5 hours one way, and any mission requires careful planning for navigation, data collection, and autonomous operation. Additionally, the small size of Pluto means precision is critical. A spacecraft must aim accurately to encounter the dwarf planet and gather meaningful scientific data. The most notable mission to Pluto is New Horizons, launched on January 19, 2006. New Horizons traveled at incredible speeds for a spacecraft, over 16 kilometers per second at launch. Yet, even at this velocity, it took about 9.5 years to reach Pluto, arriving on July 14, 2015. Its trajectory was largely a direct path, assisted by gravity assist from Jupiter in February 2007, which increased its speed and shortened the transit time. The journey covered nearly 6 billion kilometers through the cold, dark reaches of the outer solar system, requiring precise navigation and robust engineering to ensure the spacecraft survived and functioned across nearly a decade in transit. The New Horizons encounter with Pluto was historic. The spacecraft provided the first close-up images of Pluto's surface, revealing a world of mountains made of water ice, vast plains like the nitrogen ice-rich Sputnik Planitia, and intricate patterns of glaciers, craters, and tectonic features. It also imaged Pluto's moons in unprecedented detail and studied the dwarf planet's thin, layered atmosphere. These discoveries completely transformed our understanding of Pluto, showing it to be far more geologically active and complex than astronomers had ever imagined. New Horizons' 9.5-year journey to Pluto illustrates both the challenges and triumphs of deep space exploration. Even traveling at high speed, the enormous distance to Pluto meant that mission planners had to think in terms of years rather than months, coordinating launch windows, gravity assists, and navigation over interplanetary scales. This long transit also highlights the patience required for outer solar system exploration. From conception and design to data return, missions like New Horizons span more than a decade, demanding sustained commitment and precision from scientists and engineers alike. Pluto also exemplifies how exploration beyond Neptune transitions from studying planets to investigating distant, icy worlds. While Neptune required 12 years for Voyager 2 to reach, New Horizons demonstrated that with modern propulsion and planning, a slightly smaller object even farther away could be reached in under a decade. These missions collectively reveal a pattern. The farther from the Sun a target lies, the longer the journey, the greater the engineering challenge, and the more precious each opportunity for close-up observation becomes.
In essence, Pluto stands as a gateway to the Kuiper Belt, the outermost regions of our solar system, where countless small, icy worlds await discovery. Its 9.5-year journey for New Horizons emphasizes the scale of the solar system, the precision required for deep space navigation, and the incredible patience and foresight needed to explore even the most distant corners of our cosmic neighborhood. It also serves as a reminder that travel times to the outer solar system vary widely, from months to years, and that each journey, whether to Venus or Pluto, requires careful planning, ingenuity, and resilience. With Pluto explored in the context of outer solar system travel, we can now bring all these journeys together in the conclusion, summarizing the wide range of travel times from inner planets to the farthest reaches, and inviting reflection on the scope of human exploration. As we reach the conclusion of our journey across the solar system, it's remarkable to reflect on the vast differences in travel times to each planet, a range that spans from just a few months to over a decade. Starting with Venus, Earth's closest neighbor, spacecraft like Mariner 2 and subsequent missions reached it in only 4 to 6 months, taking advantage of its proximity and favorable orbital alignment. Mars, the red planet, and our top candidate for future human exploration, lies farther away, requiring 6 to 9 months of travel, depending on launch timing and trajectory. Moving beyond the inner planets, distances and travel times increased dramatically. Jupiter, the largest planet, took spacecraft like Galileo and Juno 5 to 6 years to reach, while Saturn, with its mesmerizing rings, demanded nearly 7 years of travel for the Cassini spacecraft. As we push farther into the outer solar system, the icy giants and distant worlds challenged our ingenuity even more. Uranus, the sideways rotating ice giant, was visited only by Voyager 2, which took about 8.5 years to arrive. Neptune, the farthest major planet from the Sun, also awaited Voyager 2, which required 12 years of careful navigation, gravity assist, and endurance across billions of kilometers of deep space. Finally, venturing even beyond the classical planets, Pluto, now recognized as a dwarf planet in the Kuiper Belt, was reached by New Horizons in roughly 9.5 years, revealing an icy, surprisingly complex world that had previously been just a distant dot in our telescopes. These buried travel times underscore the staggering scale of our solar system. Each mission is a triumph of engineering, physics, and human perseverance, requiring years of planning, meticulous calculations, and unwavering attention to detail. Gravity assists, launch windows, trajectory corrections, and autonomous operation all combine to turn what might seem like impossible distances into achievable voyages. From the brief 4-month journey to Venus to the 12-year trek to Neptune, these missions highlight the extremes of both proximity and remoteness in our cosmic neighborhood. The diversity in travel times also reminds us of the different challenges each planet presents. Inner planets like Venus and Mars are relatively accessible, allowing for more frequent exploration and even the possibility of human travel in the foreseeable future. The gas giants and icy worlds, by contrast, demand patience, careful planning, and technological sophistication, making each successful mission a rare and precious opportunity to expand our understanding. Beyond the planets themselves, these missions teach us about orbital mechanics, long-term spacecraft reliability, and the sheer scale of the solar system, knowledge that will be invaluable for future explorers venturing deeper into space. As we reflect on these journeys, it's awe-inspiring to realize that all these planets, from Mercury and Venus to Uranus, Neptune, and Pluto, have been touched by human-made spacecraft. Each mission, no matter how short or long, adds another chapter to the story of exploration, revealing the diversity, beauty, and complexity of our solar system. Some worlds are harsh and inhospitable. Others are icy and mysterious, and still others, like Mars, could one day become stepping stones for human settlement. So as we wrap up this cosmic tour, take a moment to imagine the possibilities. Which planet would you most like to visit if you had the chance? The volcanic plains and canyons of Mars? The spectacular rings of Saturn? The sideways rotating ice giant Uranus? Or the distant frozen world of Pluto? Each destination offers its own wonders, mysteries, and challenges, waiting for the next generation of explorers to uncover their secrets. Traveling to these planets is no longer just a dream. Through decades of careful planning, precise engineering, and relentless curiosity, humanity has already begun the journey across the solar system, turning imagination into reality, one mission at a time. The solar system is vast, the distances immense, and the challenges enormous. But as history has shown, with ingenuity, determination, and patience, no world is truly out of reach. From months to over a decade, our journeys remind us of the scale of our cosmic neighborhood and the boundless opportunities for discovery that await us.
and the next adventure could be just over the horizon. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.